When we did the energy section, we talked very briefly about electricity and how it's a form of kinetic energy because you have moving electrons. But we're going to go deeper into electricity, and we'll start today by what a charge is and how charges move from one place to another. Some of this we've already done as of yesterday, so you can kind of breeze through this real quick and just review. And then the rest of it, you can pause and take notes. And there will be a quiz in the Google Classroom as well as on my website that you can do to show me that you read and understood what we were talking about today. So just a real quick and simple review. Inside an atom, you have a proton, you have a neutron, and you have electrons. The protons and neutrons are in the very center nucleus of the atom. Protons are positively charged, neutrons are neutral. Electrons are what we're concerned with when we study electricity. They're negatively charged, and they're found on the very outside of the atoms. When we add energy to an atom, we can get those electrons to jump, either a valence level or jump completely out of the atom itself. The object, whether it's an atom or an entire object itself, that loses an electron or loses a group of electrons ends up positively charged, while the object or the atom that gains the electrons is negatively charged. Now, no matter whether we're losing or gaining, it's important to remember that electrical charge, just like energy that we've been talking about for so long, is neither created nor destroyed. It just transfers from one location to the other. So it has to come from somewhere and it has to go somewhere, but it can be transferred from one place to another or from one object to another. Now, those objects that either receive or lose the electrons, when they become charged, if they have the same charge, then they will repel each other. If they have opposite charges, then they will attract. So opposites will attract and like charges will repel. There's a couple ways to get objects to be charged. One is by conduction, and that's by directly transferring. We use the example of walking in your socks across carpet. Since your socks and the carpet are actually touching each other, you end up getting charging by conduction, by actually directly transferring those electrons from one object to the other. The other way is charging by induction. And if you look on the bottom right here, this picture, you can kind of see what induction involves. If you have a neutral object and you bring a charged object next to it, the like charges will repel, will move away from that object, and the opposite charges will be attracted to it. Then if we can separate that object and keep those charges on the side that they are at, then we end up with one positively charged and one negatively charged object without even having to touch it. Now, when we move charge, we can move it through materials that allow it to pass freely, such as conductors, metals, plasma, graphite. And sometimes we get objects that do not allow charge to move very easily. Those are insulators, such as glass, wood, plastic, cloth. Those do not allow charge to move very easily. Not that they don't allow it at all, but it's very hard for electrical charge to move through those objects. And we have that big question, well, why metals? Why are metals such good conductors? Well, it's because of their metallic bonding. When you have metallic bonding, you have individual metal nuclei, like say a whole bunch of copper atoms, held together, and they tend to share those valence electrons, those outer level electrons. They kind of become community property. They're shared between all the atoms. And so since those electrons are free, they're free to move around, they move around very easily, and it's very easy to take that energy and transfer that energy throughout your entire system and move that electricity from one side to the other. So it's very easy to conduct that electricity, that electron flow from one end of a metal to the other. Now let's talk forces. Because you know that we talked about attracting and repelling, like charges repel, opposite charges attract, but that force that's causing them to come together or causing them to push away is an electrical force. And it's important to remember that charges will exert a force on each other even over a distance. When those balloons in the picture earlier were repelling each other, they weren't touching and pushing away, they were repelling over a distance. That force that we get between charges is stronger the closer they are together. And it's also stronger the higher charge we have. One practical application of this is electrostatics. Electrostatics are used in pollution control. You have positive, in this case, in the picture down there, you have positively charged precipitators. And when you have negatively charged ash and pollution going through those precipitators, they attract those negatively charged particles of soot and pull them out of the air that's being released, and can then take that ash and that soot away safely without it going into the air and into our lungs. Also, paint droplets. Whenever you are doing a really nice finish on an automobile, sometimes you'll use a certain type of paint gun that charges those paint droplets and allows them to pretty much stick to the car. It's electrostatics. It's a static attraction between the paint droplets and the car, and that gives you a nice uniform coat. Also, copy machines. I'm running off copies for you guys all the time, and copy machines work with electrostatics. When I put my original on the copy machine takes a picture of it and creates a picture with static. And as new paper comes in, it rolls under that static picture and becomes charged by conduction. And when those pieces that are charged pass through the toner cartridge, the toner is negatively charged and it attracts to the paper and holds on tight. Then it runs through a finisher that heats it up and basically melts that toner to the paper. But it's all done with static. Isn't that interesting? So the relationship between the distance and the amount of charge and the force that we get was created or was put together by a man named Charles Coulomb. And Charles Coulomb tried different experiments to find what that relationship was. You can see the picture down here in the bottom right where he had two metal spheres, and the metal spheres were both charged differently. And what he would do is put them together and let them push each other away. They were charged similarly, charged with the same, positive or negative charge. They would push each other away. And he tried to experiment different ways with different amounts of charge and with different distances between them at the very beginning, and looked at how fast those masses accelerated away from each other. Remember, mass times acceleration is force. So by measuring the acceleration in the masses, he could calculate the force that was pushing between these objects, of course one being fixed and one allowed to move freely, and was able to find a relationship between the force, the charge on the spheres, and the distance between them, the beginning distance between them, by doing this series of experiments. So here's what we came up with. This is Coulomb's law. And Coulomb's law very simply states that the force between two charges that are separated by a distance is proportional to how much charge those objects have, and inversely proportional to the square of the distance. Now, proportional and inversely proportional, remember we talked about going up and down together, or seesaw. Proportional means they go up and down together. The force is directly proportional to the magnitude of charges. The more charge you have, the more force you have. The less charge, the less force. They go up and down together. That's proportional. Inversely proportional, think like a seesaw. If you have more distance between your objects, you'll have less force. If you have less distance, you'll have more force. The closer you get them, the more that push is between the two, either resisting or attracting. So that's Coulomb's law. Now that we knew that relationship between force and charge, now we can get a standard unit of charge. We can say, okay, this is an amount of charge. We know it's not just more or less than something else, but we can get an actual measurement to it, a number to it. And it turns out that the standard unit of charge is called the Coulomb. Imagine, he named it after himself. So the standard unit of charge is called a Coulomb, and 1 Coulomb is equal to the charge of 6.25 times 10 to the 18th electrons or protons. Electrons and protons, even though they're positive and negative, they have the same magnitude of charge. That's how they're able to balance each other out. So if you take 6.25 times 10 to the 18th of those, which is a whole lot of electrons or protons, but keep in mind how tiny they are, the magnitude of that charge would be 1 Coulomb. So how much charge does 1 electron or 1 proton have? That's called the elementary charge. And the elementary charge is equal to 1.6 times 10 to the negative 19th, a teeny, teeny, tiny number, coulombs. And that's the charge of 1 electron or 1 proton. Okay? Force between objects, when he had the two spheres and he was trying to see if they were pushing or pulling, force is a vector. It has both a magnitude and a direction. He found the amount of force, and you could also find which direction that force was going, if it was pulling or pushing. It turns out that positive things are pushing, negative things are pulling inwards. And so when you look at these field lines, you can kind of start to see, looking at the direction of those field lines, why your opposites attract. Positive is pushing out and the negative is pulling in. So those will attract each other. But if you have two positives or two negatives, they're going to be pushing against each other and you'll have that repelling motion. Electrical fields are the representation of the force around an electric charge. And your electric field depends on the magnitude of the charge itself and the size of that charge. So when you're drawing field lines, even though on here you have the red positive and the blue negative, and you see them all radiating out 360 degrees, remember it's even more than that. Your charge is like a sphere. So you've got charged field lines coming out towards you, out this way, out that way, back to the back. It's going all around in 3 dimensions. Okay, so the lines that are drawn around the charge that we draw will show the direction and the strength of the force. The one on the top over here between the positive and negative, the field lines are widely spaced, so it's not a very strong force between the two. However, the picture on the bottom with your two positive charges is very strong. You have two very strong charges that are pushing, that are repelling each other, very strong. And again, remember that this electric field happens in 3 dimensions. It's not just 2 dimensions on paper. It's coming out at you and back into the paper. So static. When we have a bunch of charge built up on an object, you get static electricity. And you've experienced this before at some point in your life, I'm sure. You walk across carpet in your socks, or you get clothes fresh out of the dryer, or you're under a wool blanket in the wintertime. When you have that buildup of charge, that's static electricity. When we get that buildup, if you want to quantify it, we have what's called the electric potential difference. An electric potential difference, think of like potential energy. With gravitational potential energy, we talked about how the higher your object is, the more height it has above the Earth's surface, the more potential energy it has. Potential difference is very, very similar. The further away your charges are from each other, the more potential energy, potential difference, is between them. And so that potential difference is kind of like gravity pulling down. It's that force pulling your electrons together. And we can find electric potential difference by taking the work done moving a charge in a field and dividing it by the magnitude of that charge itself. Electric potential difference is in joules. Joules is work, and so we're talking about the amount of work done to move a charge. So joules per coulomb. Okay, so amount of work it takes per charge, joules per coulomb. And 1 joule per coulomb is simplified to a volt. Have you heard the word volt before? Electric potential difference is very simply known as voltage. So when you're thinking about the voltage of a light or of a cell phone charger or whatnot, the voltage is the amount of electric potential difference, the potential energy of that electrical charge. Now, when we have static built up, when we have that electric potential difference, that's not a happy state. Just like your books are wanting to fall off the shelf, your charges are wanting to be with the other charges. And everything is wanting to be a nice balanced state where you don't have any of that potential energy stored in your system. So a process called grounding will take that extra charge and remove it. It can either be safe, like in the case of this oil tanker that's filling up a gas station, and so it attached the hook to the ground and allowed those extra charges to flow out gently. Or it can be a little bit more violent, like lightning. So whether or not it's violent or safe, your grounding is still going to take that extra potential difference and remove it from our system. So that's going to conclude static, which is that one-time bounce of energy from one place to another. With the next section, we're going to talk about current electricity, where we take that electric potential difference, that voltage, and let it flow constantly so that we can put it to use. So that's where we're going to stop today. Make sure you take your quiz, and I'll see you next time.